Thank you. My name is Patrick Lee. So this is work on STAIR code. And this is joint work with Mingqiang Lee. He's my postdoc. And so he came up with all these ideas and evaluation, and credit should go to him. To begin with, the motivation is storage systems are susceptible to both the device and setter failures. And by device failure, I mean data loss in entire device, and setter failures, maybe you have data loss in a particular setter within a device. So actually, there are a lot of field measurements showing the severity of these device and setter failures. So it shows that actually the annual disk failure rate is up from 1 to even 10%, which is very huge if you consider a large number of disks. So this number is very huge. And also, setter failures are quite common. It is even more frequent than disk failures. And people also call this the latent setter errors. And also, the studies show that actually these setter failures can come in bursts. We see that actually there's some burst length which is even more than 5. Okay, although in most cases it's 1 or 2. So the question is, how do we tolerate these device and setter failures to make sure that our data is still available? So in here we look at using the solution based on erasure coding. The idea is to add some redundancy to the data. And here we look at a code called the systematic MDS codes, which we define this by two parameters, n and k. What that means is that given k data pieces, we encode them to create n minus k, what we call the parity pieces, and the total of n pieces will be distributed across the disk. And the nice property about these MDS codes is any k out of n pieces can recover the original k data pieces, and of course the n minus k parity pieces. And so that will provide a fault tolerance. Just so you know, systematic means that the original data is still there after you do the encoding. You don't need to worry about these notations n and k for now, and we will come back to that when we give you examples. And here we look at 3 erasure coding schemes: traditional RAID or erasure coding, intra-device redundancy, and setter disk codes. And we will see how they tolerate both the device and setter failures. So we start with an example to illustrate how they work. Here we look at a mixed failure scenario where there are m entirely failed device and m prime partially failed devices. You may need to remember what m and m prime means here. Okay, so we set m equals to 1 and m prime equals to 2 to denote the partially failed devices. And in particular, we set these devices have, one of them have 1 setter failure and the other one has 3 setter failures. So we can map this to n equals to 8 devices. And usually we would divide the data into different groups, which we call the stripes. So each stripe will be encoded independently. And in here, when we do the encoding, we work on the setter level. So each of these square denotes a particular setter. And the question is, how do we efficiently tolerate such a mixed failure scenario using erasure coding? And by the way, this works, although looks at the disk array scenario, actually it could also be applied to general distributed storage systems where these devices are mapped to the storage nodes and the setters mapped to blocks. Or to the SSD, we know that the SSD will wear down, so we can map the setter to this block to provide the fault tolerance. So we will see how the erasure codes work. Okay, let's look at the traditional case. The main idea of traditional RAID or erasure codes is it only provides device level tolerance. So what that means is that if you want to tolerate the entirely failed device and also partially failed device, you have to dedicate parity devices to tolerate all of them. So even though you just want to tolerate one single failed setter, but you need to dedicate the whole parity device to protect that. So from our previous mixed failure scenario, we need 3 parity devices to do that. And that actually is an overkill because use 2 parity devices to tolerate 2 partially failed devices. And the main reason is that they only provide device level tolerance. Now, there's another proposal based on called the Intra-Device Redundancy. So the main idea is that you protect each device by adding some parity setters. So because we want to protect a burst of setter failures of length 3. So in this case, we add 3 parity setters to each stripe so that you put all the parity setters across all the data device. And actually, this is also very expensive. The reason is that the parity setters only protect one particular device, but it doesn't know the presence of the other devices. So here is also costs a lot of storage overhead. Last year, Professor Planck proposed the SD code. So the main idea is to provide a space-efficient erasure code to protect both the failed devices and also the failed setters. So it uses 2 parameters, M, where it can tolerate M entirely failed devices, and there's also S failed setters in each stripe. So in addition to these failed devices, we also want to protect the failed devices, failed setters. So usually this is how it puts the parity disk and also the parity setters. So here we put the parity devices here and also the parity setters inside a stripe. And the current construction is basically limited to S less than equal to 3. So the question is, how do we tolerate our previous example on the mixed failure scenario? So in this case, because we assume that there are a total of 4 setter failures, so in this case, we need to dedicate 4 parity setters in this stripe. But unfortunately, this construction is not available at this moment. So our goal here is to construct a general space-efficient family of erasure codes to tolerate both the device and setter failures. And by general, what it means is that we don't want to put any restriction on the size of the storage array, the number of devices. And also, we don't put restriction on the number of tolerable device failures, that is the M. And also, we don't want to put the restriction on the number of tolerable setter failures. And by space efficient, it means that we put some parity setters, the number should be equal to the number of setter failures that you want to protect, just like SD code. So that's why we came up with this, what we call the STAIR codes. So the building blocks of these STAIR codes are the following. So the first one is we define a setter failure coverage vector. Basically, it defines a pattern of how the setter failures occur rather than how many setter failures occur as in SD codes. We will come into that in a moment. And also, if you are able to define this setter failure coverage vector, then you can define the code structure, which actually is built on 2 encoding phases, and each encoding phase is built on an MDS code. Any MDS code will work, and in our case, we use the Cauchy-Resolvent. But as long as the parameters are supported, then you can use that MDS code. And based on this code structure, we propose 2 encoding methods, upstairs encoding and downstairs encodings. And there's a nice property that it reuses the computer parity results in the encoding so that you can improve the encoding performance. And actually, they are complementary to each other. And we'll see how they work. So let's look at the setter failure coverage vector. So SD code defined a parameter called S. So the idea is it can tolerate any combination of S setter failures per stripe. And the current limit construction will be limited to S equal to 3. Now what STAIR codes do is to define a failure coverage vector given by this E, which is composed of E0, E1 up to EM prime minus 1. So M prime will be the number of partially failed devices that you will consider to have the setter failures, aside the device failures. Okay, so you provide some parameter to bound the number of partially failed devices, And then in each such device, you try to bound the number of setup failures. E0 means that one device have E0 setup failures, and E1 means one other device have E1 failures. And without loss of generality, we just arrange them in increasing order. And the sum of these elements will be equal to S, which is the total number of setup failures per stripe. And the rationale of this is because we see that the setup failures will come in small bursts, so you may want to define a small m prime to define the number of partially failed device and also a reasonable size of error for the burst. So let me show you an example to see how we define this vector. So going back to our previous example, because we want to tolerate two partially failed devices, so in here we define a vector of length 2. And here we set E equals to 1, 3, which means that at most two devices aside this entirely failed device will have the setup failures. So one of these partially failed devices will have at most three setup failures that I can tolerate, and another one will have at most one setup failure that I can tolerate. Okay. And by the way, I just defined the number in here. It doesn't have to be sequential. So within a stripe, I can tolerate any number of 3 setup failures per device within the stripe. So if we understand this setup failure coverage vector, then everything else will be quite intuitive. So the goal here is we want to form this parity layout. The main idea is within the data stripe, so the green colors are some data setters. We have also the parity device and also some other parity setters, which we call them the global parity setters. We'll see in a moment what we mean by global. Now the question is, how do we generate these global parity setters as well as M1 parity device? And the idea is to use two MDS codes, C row and C column. Okay, so these MDS codes could be any constructions. For in our work, we use Cauchy-Solomon codes. So let's see how this works. Okay, so the idea is that C row, what it means is we do the encoding along the row direction. So in the first phase, what we do is in each row, we encode the data to form the parity device as well as the intermediate parities, while the number of columns of here will be equal to the number of parity device, which is 1 in here, and also the number of plus the number of partially failed devices, which is 2 in this case. So the first thing we do is we generate all these parities. Now the parity device will be used to protect the device failure. Now what the intermediate parities do is to do the second phase, which we further encode them to form the global parity setters. So in here, the C column basically will do the encoding along the column directions, and you will generate all these global parity setters. Usually you can construct a code that can generate the maximum number of setup failures, and the other one are dummy, then you don't need them. So why we call them the global parity setters? The reason is each of these global parity setters is a function of these intermediate parity setters. And each of these intermediate parity setters is a function of the row of the data setters. So you can see that actually this global parity setters is a function of all these data setters. So that's why we call it global. So these global parity setters will be used to protect the setup failures. Now the question is, how do we move these global parity setters inside stripe? You have to find ways to store them. Okay, so we need to find ways to put them inside the stripes, and the main idea is we treat them as zeros, and we treat 4 of these data setters as lost setters. And the goal is you just reconstruct them. Just treat them as failed setters and then reconstruct them. So once you construct them, you don't need to store them anymore because you know them, they are equal to zeros values. So the question is, given this setting, how do we compute these inside global parity setters? And what we do in here is we augment the stripe to add some augmented rows. Okay, so here we add some virtual rows in here. And how do we form these virtual rows? So what we do is we encode each column using C column to form this augmented row. So each column we form these virtual augmented rows in here. So we form a larger stripe. We call this the canonical stripe in the paper. But the larger stripe will enable us to compute these inside parity symbols. And one nice thing about this is each augmented row is a code word of 0. What that means is that the upper rows, you can use the 0 to do the encoding and decoding. And actually, in these augmented rows, you can also use 0s to do the encoding. The reason is because of this linear property. What it means is that after you do the encoding of using the C column, actually you will still preserve the code structure of the 0 because they are just some linear combinations. The proof is in the paper, so I will refer you to the details. But based on this property, we will do this reconstruction. So let's start with the first one. We call this the upstairs encoding. Basically, the idea is the same for decoding, so you can use the same approach to recover the failures. So the idea is that you do it in an upstairs manner, so you start from left to right and then bottom to up. So the first thing is we construct these parity symbols. Now the 0 here is 10-7 code. What it means is any 7 setters can reconstruct 10 setters. And the C column basically means that any 4 out of 7 any 4 setters can reconstruct all the 7 setters. So as long as you have enough number of setters, you can reconstruct the remaining setters using the code. So here we look at the column direction. We have 4 data setters here, so we can reconstruct the remaining 3. Same thing for step 2, step 3, step 4, and step 5. Now, if you notice this row in here, the first augmented row, right now we have 7 setters available. The one that we computed, and also the zeros that we set earlier. So we have enough setters, so we can reconstruct these data setters. Now, if you look at this column, right now we have 1, 2, 3, and 4. So we have enough setters again, so we can reconstruct the setters here, which is the step 7. And then the thing is step 8, because we have enough number of setters, and step 9, and then go to step 10, and finally will be the remaining setters in the parity device. And one nice thing about this is the parity computation will reuse the previously computed parities. So so it's not just directly computed from all the data setters, but in fact you can use the previous computed parities to do the computation. That will improve your encoding performance. We'll see in a moment in the evaluation. Downstairs encoding means that you do this from top to bottom and right to left. This approach can be used for encoding, but we cannot generalize this for decoding because of the way of how we define E, which again you can refer the details to the paper. So the idea is you start with along this first row, again because you have 7 setters, so you can reconstruct the remaining 3. So, and then you do the step 2 because right now you have this one, and also you have the other 3. So you have 4 setters, so you can reconstruct the other 3. And similarly, you can do step 3, step 4, and then step 5, which again switch to the column direction, step 6, and eventually you will compute all these parities. So this is how it works, and we can show that actually it can provide the fault tolerance that we want. So again, also like the upstairs encoding, we use this parity reuse feature to speed up the encoding performance. So actually, we can see these 2 approaches, they actually will return the same result, but you start from different point to do the encoding. So eventually, you will get the same result, but actually, they have different encoding performance. So actually, we in the paper, we did some calculation, and we showed that what is the right time to choose which coding. And the intuition is that if M prime is large, you should choose upstairs encoding, and for M prime is small, then you choose the downstairs encodings. Again, the details are in the paper. So let's take a look at some evaluation results. We implement the code which is built on Erasure and also GF Complete, developed by Professor Jim Plang. And we do the experiments on a multi-core machine with the SSE support for the GF Complete library. And we also do the comparison with the traditional resolving code, which just provide the device level failure tolerance and also the SD code. And we will see different metrics, storage savings, encoding speed, and also the update cost. So the first one is the storage space saving. So in here, we compare with the traditional erasure codes that just use the device level fault tolerance. So the x-axis here is the chunk size. What it means is the number of setters in a stripe. So we vary this parameter. The y-axis here is the number of devices that I can save compared to the traditional erasure codes. So we configure different number of S, and accordingly the vector E, and also the M prime, the number of partially failed devices. The main idea is that as R increases, the number of devices saved will be approximately equal to M prime, which is intuitive because traditionally, in using the traditional erasure code, you need M prime priority devices to provide the tolerance against the setter failures. But right now, we just use a single parity setter to do the job. So that's why it will approach M prime as R increases. Now, another one is the encoding performance, which we compare with the SD codes. So the x-axis is the number of devices, and the y-axis is in the encoding speed, which is in megabytes per second. We see that actually the encoding speed of STAIR codes is on the order of over 1,000 of megabytes per second, which we think it should be fast enough compared to the our speed today of today's disk. And also, compared to SD code, we see that we can significantly improve the encoding speed. The main reason is that we use the parity when we do the computation. While in the SD code here, we assume that it's based on encoding from the data setters. And the similar results also apply to the decoding. One main point is that in here we consider the worst case, but in general, you may just lose one setter at a time. So you don't need to read all the parities to recover that failed setter. You can just use the same row, the parity setters of the same row, and then you will do the recovery. So in general, the decoding speed should be much, much faster than the encoding speed. And also, we look at the update cost. It's defined as the number of updated parity setters when you update one data setter. So we update each data setter, we computed the average over all the data setters. So the x-axis is different coding scheme. We look at our resolving SD code and also STAIR code. In STAIR code here, if you configure an S, so there may be different combinations of E. So we pick the worst one and put the figure in here. So the y-axis is the update penalty. So we see that actually we are quite close to SD code. We may be a little bit higher, but it's just because of different ways to construct the code. But in general, if you look at the deviation, actually they overlap. But the thing is, both of them are more expensive than resolving code, which is understandable because you not only need to update the parity setters, the parity device, but also the parity setters. But it will be good for the systems if you're doing backup or the full stripe write, such as in SSD. So here comes the conclusions. So we propose the STAIR codes. It's a general family of erasure codes for tolerating both the device and setter failures in a space-efficient manner. And we propose two encoding methods which provide complementary performance. And we advocate open source, so we publish the source code of STAIR code, and you can just download it from this link, and you can play around and see if you can get some insights from there. Okay, thank you. I appreciate it for your questions.
Do you ever worry about the cost of accessing those extra sectors, the ones you have to recreate every time? So if you're doing random I/O on your RAID device and you say I need that sector and it's one of those special ones that's encoded, then you'd have to turn around and read the whole full stripe to recompute that. So I don't know if you have even a way of usefully measuring that overhead.
Basically, you need to read the full stripe because the way we do the upstairs encoding and downstairs encoding. You need to read through the whole stripe to reconstruct a particular lost field center. Yeah.
Umesh from Nimble Storage. So it seems like one of your assumptions is that sector errors often happen in bursts. And I don't know whether it's an assumption or just a case that you take care of. And the reason I'm pointing it out is that, so that may be true for hard disks. For SSDs, the errors may be randomly distributed. So when it's randomly distributed, you might want what you call your E vector to be sort of flat.
Right.
And would that be just a degenerate case of what you're providing, or would that be something difficult?
This is the case we try to address. So in your case, if you have spread out, then you can just devise a factor just like 1, 1, 1, 1, 1.
Yeah.
And we are not, so about the burst case, it's just a case that we address. We just want to provide more general combinations.
Got it.
Yeah.
Okay, great. Thank you.
Thank you.